Hello, I'm going to record a series of short videos, vodcasts, on the topic of stoichiometry, which is the kind of technical scientific name really for most of what you're studying this unit, counting particles. I'm going to start with a review of previous knowledge. We're going to look at atomic structure. And our example will be the very popular element carbon. You'll be coming across a lot of carbon in this course. So carbon is an atom. Well, you have an atom of carbon. Every element on the periodic table has an atom of that element. And like all atoms, it has a nucleus with 6 protons and 6 neutrons. And in a neutral atom, at least 6 electrons. The protons and the neutrons, collectively known as nucleons, are found in the nucleus, whereas the electrons are found in the orbits or shells that surround the nucleus. And one way of representing this is the symbol that you see in front of you, the little diagram, which has the C for carbon, the 6 and 12. Now that C is the element symbol. That's given the generic name of X if we're talking about what these things represent. So C for carbon, O for oxygen, H for hydrogen. 6 is the atomic number, Z. That is the number, it's a count, it's the number of protons in the nucleus. And the most important thing there is that the number of protons in the nucleus determines what element that atom is. So the element symbol and the atomic number are kind of tautological. One tells you the other. If it's carbon, it's 6. If it's 6, it's carbon. The symbols are a bit easier to remember, really, than trying to remember all the atomic numbers there. Finally, we have the mass number. This is also a count. It's a count of the number of nucleons. The important word there in mass number is number. It's the number of nucleons. So in other words, it's the number of protons plus the number of neutrons. And since you know the number of protons, that's the atomic number, you can work out the number of neutrons. So here we have 6 protons and a mass number of 12, so 12 nucleons. So we must also have, as we have said, 6 neutrons. It's important to make that determination because not all carbon atoms have that number of neutrons. Instead, you can have different isotopes of different elements. So here we have 2 other examples of isotopes of carbon. We have carbon 13 and carbon 14. Now carbon 12 is by far the most common isotope of carbon, and that's the way we say it, by the way. If we're identifying different isotopes, we say the name of the element and then followed by the number, the mass number of that isotope. So they all have the same atomic number, 6, because they're all carbon, but they have different mass numbers. So carbon 12 forms 98.89% of all carbon. Carbon 13, 1.11% of all carbon, and carbon 14, a very, very small amount. It's radioactive, which is a fraction of a percent. Now, in your periodic table, you will see a chart that looks something like this, or more likely something like this, which is the element. Again, it's carbon. Again, it's got the atomic number, Z, which in this case is 6. The number at the bottom is the relative atomic mass. This is subtly different to the mass number. So the mass number, as we've said, is the number of protons plus the number of neutrons, whereas the relative atomic mass is the average actual mass of an atom of that element. This is a difficult distinction to make. One is a count, just how many protons and neutrons, and can only ever be a whole number, and it depends on the isotope. So carbon has 12, carbon 12 has 12, carbon 13 has 13, carbon 14 has 14. Whereas the other is a unit of mass, or weight if you prefer, and is in atomic mass units. Now atomic mass units are approximately equal to the weight of a proton or a neutron. Protons and neutrons weigh almost exactly the same, not totally, but almost exactly the same. And the atomic mass unit U, which is a number based on around carbon, a 12th of a carbon 12 isotope. So it's approximately the same. So the 2 numbers are often very similar numbers, but they're not the same number. So 12.011, and that, by the way, is also the average, taking all of these percentages into account. Those percentages, by the way, might vary from place to place, but on Earth, those are the standard percentages. Okay, so that's relative atomic mass, and it's the relative atomic mass that you'll be using throughout the rest of this unit in almost all cases. How you use it is something that we'll look at in the next video when we look at the mole.